All right, in this video, we are going to talk a little bit about some imaginary and complex numbers. I'm actually going to change the title of this. We'll call this Intro to Imaginary Numbers, also sometimes called complex numbers. So this begins the 12-day journey of while I'm outside of, or while I'm not here in class for the birth of my child. So I hope that you guys can stay on track here with these videos. Again, everything's going to be on Edpuzzle, and then there will typically be either some worksheet practice or some practice within the OneNote here. So just make sure you're looking at that plan that I've shared with you guys on Google Classroom and that Google Doc, and you should be able to keep up to speed there. So let's begin this video. First question, when you hear imaginary numbers, let's talk first about where do they come from? Okay, so where do imaginary numbers come from? All right, so imaginary numbers, maybe you've heard of these before. Imaginary numbers come from when we take the square root of negative numbers, okay? Just a reminder, you should be writing things down as you watch these videos, because when you guys take your quizzes for this unit, I'm going to allow you to use any notes and written homework that you've done as you're taking the quiz. So everything that I write down here, you should be trying to write down as well, so that you can keep track of things for when you get to a quiz. All right, so for example, if we wanted to think of something that was imaginary, if I took the square root of -9, this is imaginary because there are no numbers in the world that I can take no negative numbers that I can take the square root of to get an answer. And for example, if I took any number in the world, positive or negative, and I square it, I'm always going to get a positive number. So no matter what, I'm not going to be able to take the square root of a negative number. One way where you might see this at play, if we had some sort of function like f of x equals the square root of x minus 3. We talked about this earlier in the year. If I told you to find the domain of this function, well, we've said, hey, I can only take the square root of 0 or positive numbers. So therefore, if this thing underneath the radical cannot be negative, that means that this function, or what's underneath that radical, has to be greater than or equal to 0. That way it's not negative. And so therefore, in this function, all x values have to be greater than or equal to 3. And if you were to sketch a graph of this, maybe you've done this in Algebra 2, maybe you haven't. This function actually starts at x equals 3, and it would look like this. And the reason why it only exists to the right of 3 is, again, if you pick something that was less than 3, like for example, let's say you picked 2, and you tried to plug it into the function, f of 2 would be the square root of 2 minus 3, and that's the square root of -1, and we cannot graph that on a number line, therefore it doesn't exist within the function. However, just because you can't graph it on a number line doesn't mean that you can't do any math with it, and that's where this idea of imaginary numbers comes from. So next up, let's talk a little bit about the symbol that we use for imaginary numbers. Sorry, I have myself enough space here. Okay, so all you really need to know to do anything with imaginary numbers is you need to know that I, which is the symbol for imaginary numbers, is equal to the square root of -1. So if we go back, for example, to the square root of -9, a lot of you guys will do this in your head, but what this breaks down into is the square root of 9 times the square root of -1. So we say, hey, the square root of -9 is, well, the square root of 9 is 3, and the square root of -1 is I. So the square root of -9 is equal to 3i. Okay? We could do this with some more complicated ones. So for example, if we had something like the square root of -12, a way that we could break this thing down is we could say, okay, well, the square root of 12 times the square root of -1. The square root of 12 breaks down into the square root of 4 times the square root of 3. And then we already know, hey, the square root of -1 is I. And the square root of 4 is 2. Typically, we will put the I in between this number at the front and the radical. So we're going to write this as 2 times I times the square root of 3. And the reason why we do that is because this is a very small math thing. But if you don't put that I in between the 2 and the square root of 3, students are doing this really fast. Sometimes they'll do something like this, and I can't tell, hey, is that I underneath the radical or is it outside of the radical? It needs to be outside of the radical. So in order to eliminate any guesswork there, we will just put the I in between the 2 and the square root of 3. Okay? So we can simplify square roots that have negative numbers underneath. The only thing that we have to remember is that we just have an I in our answer as we're simplifying it. And I guess one other thing I can mention is even if you had something like the square root of negative 7, you could write this. Even though the square root of 7 doesn't break down at all, you could still write this as I times the square root of 7, and that would be perfectly fine. Okay, this is another side note, something that might go over some of you guys' heads, and this is okay if it does. It's not that big a deal. But I do want to talk about, I wrote this down at the beginning of class and kind of changed the title, but there is in math something called complex numbers. And so I do want to just briefly touch on this idea of complex numbers. Do my best to explain it for you guys here. So any number in the world, I'm just going to put this here. Any number in the world is a complex number. So every number that you've ever seen in your entire life is a complex number. It's just you don't really realize that it's a complex number because we don't always have to mention it this way. So all complex numbers look like this: a plus b times I. Okay, and they all have all complex numbers have two components to it. This part at the front that's not attached to an I, we call this the real component. Most of the numbers that you've seen in your life up to this point are real numbers, ones that don't include an I. And then this part at the end is what we call the imaginary component. Okay, so all complex numbers have a real component and an imaginary component. And so if you broke this down into a box, like if I drew a box right here, and this is all the numbers in the entire world, all the numbers in the entire world are broken down into either a real number or an imaginary number. And again, most of the numbers that you've seen in your life up to this point are real numbers. And so, like, if we just pick some real numbers, like some numbers that we're used to seeing, let's say we had 5, and let's say we had pi, and let's say we had 1/2, and let's say that we had 1 million. Okay, well, these are all real numbers. They have this imaginary component at the end, but guess what? The number in front of the I, if it's a real number, that number is a 0. Okay, so this is just going to be for all of these real numbers, it's just going to be plus 0I. And the reason why we don't write that all the time is because obviously that would get rather redundant. And additionally, that part at the end of the plus 0I, well, 0 times anything is 0. So that imaginary component, this part right here, goes away in a real number because the imaginary part is being multiplied by 0. Okay, so we could write all of these numbers. Any number that you ever see that doesn't have an I, you could write it with an I as long as you put a 0 in front of it. That's a real number. But then an imaginary number is some kind of real number, but the part at the end that has the I, well, it has a non-zero number in front of it. So I don't know, 3 plus 7I. That's an imaginary number. If it has an imaginary component at the end, we call that an imaginary number. So 3 plus 7I, I don't know, we could have pi squared plus, we could do pi squared plus 3/5 I. Okay, that's an imaginary number. So as long as that imaginary component is non-zero, then we call that entire thing, we call it an imaginary number. And if that imaginary component at the end has a 0 as a coefficient, then we call it a real number. But every single number you've ever seen in the world falls into this box right here, and we call this box complex numbers. Okay, they either have to be real numbers or imaginary numbers. All right, that's not my main focus of today, but I did want to mention it in case you ever see the term complex numbers. Don't be confused by it. It just means, hey, it's either a real number or an imaginary number. All right, so let's talk a little bit more about I. Okay, we mentioned it earlier. I'm going to go back. So the number I, or the letter I, has a pattern, and I want us to see if we can identify what that pattern is. Okay, and I'm going to help us out here with the beginning of it, but I want to see if you can understand it as we go along. So here's how I'm going to start this pattern. I is equal to the square root of -1. And this is going to be weird, but I'm going to say, hey, the square root of -1 is I. Okay, so essentially what I'm saying here is I, and I'll switch the colors here for the end of each step. I is equal to I. Okay. All right, now let's go to the next power. The next power would be I squared. So let's think about I squared. Well, I squared is just the square root of -1, and the whole thing squared. Well, what have we learned this year about when we take a square root and square it? What happens? Well, essentially these things get canceled out. And when I'm done, I'm left with what's underneath the radical, which in this case would be -1. Okay, so I is equal to I, and I squared is equal to -1. All right, on to the next one. Next one would be I cubed. Okay. All right, well, let me go off to the side here, and let's do a little math note. All right, so you've learned this, not necessarily in my class, but you definitely learned this in pre-algebra, algebra 1, and algebra 2, and geometry. If I take something like x squared and I multiply it by, I don't know, say x to the 5th, what do I do with these exponents? Well, if this is 2x's and then this is 5x's and I'm multiplying them all together, well, what am I doing? I'm multiplying 7x's together. So what I do here is I take the exponents and I add them, okay? And why am I saying that? Well, the reason why I'm saying that is because I cubed is the same thing as I squared times, well, how do I go from 2 to 3? I add 1. So this is like I squared times I to the 1st, okay? And what did we just learn? Well, we just learned that I squared is -1. And we said earlier that when it comes to I, we're just going to call that I. So -1 times I is -I. So that means that anytime you see an I cubed, you can replace an I cubed with a -I. Okay. All right. Next up, what about I to the 4th? Well, there's a few different ways you could approach I to the 4th, but the easiest way to do this would be to say, well, I to the 4th is I squared times, well, how do I get from 2 to 4? I add 2, so it's I squared times I squared. Okay, so I squared times I squared, that adds up to I to the 4th, and we've learned, hey, I squared is -1, and I squared is -1, so -1 times -1 is +1. Okay, so here's how the pattern is going so far. I is I squared is -1, I cubed is -I, and then I to the 4th is 1. Okay, all right, let's go one more here, a couple more, and let's see if we start to see a pattern emerge. Let's start I to the 5th. Well, the best way to approach I to the 5th would be, all right, well, let's start at I to the 4th. And then how do I go from 4 to 5? Well, I add 1. Okay, why am I doing this? Well, I just learned that I to the 4th is 1. Okay, and then I, well, we've said, hey, we're just going to call I. So 1 times I is I. So I to the 5th is I. Okay, all right, one more here, and then let's see if we see a pattern. I to the 6th. Okay, I to the 6th. The really easy way to approach this, it's I to the 4th times, well, how do I go from 4 to 6? I add 2, so this is times I squared. Why am I doing this? Well, I to the 4th is 1. And we learned earlier that I squared, if you look up here, I squared is -1. So 1 times -1 is -1. All right, some of you guys are probably looking at this and saying, oh, I see the pattern here. Okay, here's the pattern. Check this out. It goes I, -1, -I, 1. And then it starts over. I, -1. Bet some of you guys could think, hey, I to the 7th. What's I to the 7th? Well, it seems like it's just fitting into this pattern here. It's a -I. And then if I tried I to the 8th, I to the 8th would end this pattern at 1. Okay? So again, if we think back here, up at the top, it goes I, -1, -I, 1. I, -1, -I, 1. Okay, so you should write this off to the side here. It goes I, -1, -I, 1. And then the pattern repeats. Okay? So if we know that this pattern repeats, and again, math is all about patterns. You probably hear me say that a lot this year. If you can identify patterns, well then math is a piece of cake. And that's all that's happening right here is we just see a pattern that repeats after every 4 iterations of I. So let's see if you guys can apply this, or we can apply this in the context of something a little bit more difficult. So let's say we had like I to the 17th. Okay, how could we approach something like I to the 17th? Well, I to the 17th, I'm going to do another little math note off to the side right here. Let's say that instead of doing something like x squared times x to the 5th, let's say that instead I was doing something like x squared raised to the 5th. Okay. Well, if you think about what this means, when I raise something to the fifth power, that means I'm multiplying it by itself 5 times. Okay. And we just talked about, well, in this instance right here, we take all these exponents and we add them together. Well, that means I'm adding 2 together 5 times, which gives me x to the 10th. Obviously, I'm not going to want to write it this way every time. That would take forever. So what's a faster way to do it? Well, just take this number and multiply it by this number. 2 times 5 gives me this 10 right here. Okay. Why am I saying that? Well, a super, super, super easy way to approach something like I to the 17th is to say, all right, well, let's start with I to the fourth. Why am I starting with I to the fourth? Well, I to the fourth is 1. And guess what? If I raise 1 to any power in the world, I'm still going to get 1. So if I wanted to approach I to the 17th, I could write this as I to the fourth raised to the fourth, because guess what? 4 times 4 is 16, and then there's only one I left over. So this entire thing right here is 1 times I to the 17th is just equal to I. Okay, because it fits somewhere into this pattern, and it just so happens to fit at the beginning of the pattern here at I, and then it goes -1, -I1, and then it repeats itself again. Well, this is the first iteration of the pattern, so I to the 17th is I. Okay, let's try another one here. Let's say that we were going to do I to the 83rd power. Okay, well, again, we're going to want to start at I to the fourth. And here's what I'm thinking about. What can I multiply 4 by to get really close, but maybe a little bit less than 83? Well, I can multiply 4 times 20, okay? Because 4 times 20 gives me 80, and then there are 3 i's left over. Okay, well, as long as I know, hey, this part right here is 1, this is 1 times I cubed, and if you know the pattern, or if you need to go back and look at the pattern, I cubed is equal to -I. Okay, so this becomes 1 times -I, and 1 times -I is just going to be -I. Okay, so I to the 83rd is equal to I to the 17th is equal to positive I. Let's try real quick. One more, we'll try I to the 34th. Okay, if you want to pause, you're going to try this on your own, you can. I'll finish it here in just a second. This is going to become I to the fourth raised to, let's think, 4 times what gets me pretty close, but a little bit less than 34. Multiplication tables are important here. I to the fourth raised to the eighth. 4 times 8 is 32. And then there are 2 i's left over, so that would be an I squared. Well, I to the fourth raised to any power is 1. And we learned earlier that I squared is -1. So 1 times -1 is -1. Okay? So I to the 34th is equal to -1. So this is what we call the pattern of I. Again, it repeats after every 4 iterations, and the pattern is just I, -1, -I1, and then it repeats itself. Okay, so we're working through that a little bit here. Now, let's put all these pieces together, and let's do a little bit of work with some expressions. Okay, so I'm going to do probably 4 of these little examples real quick. These aren't going to take very long. And then I will include some practice for you guys here in the OneNote so that you can try some of these as well. All right, so let's simplify. These first 2 that I do are going to be a little bit easier. Let's say that I gave you this, 10I times 2 minus 5I inside of parentheses, and I told you to simplify this. Okay. All right. Well, we've learned, hey, if you have something on the outside of parentheses, what should we do? We should see if we can distribute it, and we can here. So let's try this. 10I times 2 is 20I minus, because we got 10 times a negative. Okay. So 10 times 5 is 50. And then don't forget about this. I times I is I squared. Okay, we never want to leave an I to any power higher than 1 in an expression anywhere, which is the whole reason we were just talking about that pattern. So if you notice here, I have an I squared, and that I squared can be replaced with a -1. Okay, so let's think about what this will look like when we're finished. 20I, can't do anything with that, but -50 times -1 is a positive 50. Okay. So last but not least, I would accept this as a final answer, but typically, we talked about this earlier with the complex numbers, you write the real component first, and then you put the imaginary component at the end. So this would be 50 plus 20i. So that's a simplified form of that expression right there. Okay. All right, let's try one more. Let's say, and this is a super easy one, although it sometimes confuses folks, so that's why I'm going to put it here. 8 plus 7i inside of parentheses minus 3 minus 4i inside of parentheses. Okay. All right, big mistake that I see people make. They say, okay, well, I see a set of parentheses here and a set of parentheses here. That must mean that I have to multiply them out. Not necessarily, because what are these separated by? They're separated by a subtraction sign. So the only thing that we're going to distribute here is this negative sign. Okay, and if you think about it, there's an invisible positive sign on the outside of these parentheses. So technically, these parentheses on these first two terms don't really matter. So I can just write that as 8 plus 7i. But then with these last two terms, I can distribute that negative. So this is going to be a minus 3, and then a negative 4i turns into a plus 4i. There's not a whole lot else to do right here except for combine like terms. We have an 8 minus 3, so that's 5. And then 7i plus 4i is a plus 11i. So there's my final answer for this one when I distribute and I combine those distribute that negative and then combine the like terms. All right, a couple harder ones here, and we will be done with the video. And then, like I said, I'll have a little bit of practice for you guys to try. So let's say that we had 3i to the 23rd times 2 minus 7i. Okay. All right. So if I was going to approach this, anytime I see something that has an I to a power other than 1, the very first thing I should do is let's see if we can work with that at all. So let's try I to the 23rd. So let's do what we were doing earlier. Let's start with I to the 4th. And let's see, can we raise that to a power that's close to 23, but maybe a little bit less. So I could raise this to the 5th power because I to the 4th raised to the 5th. 4 times 5 is 20. That leaves me with an I cubed left over. Okay, so this is now 1 times I cubed. If you look at your pattern, again, it goes I, negative 1, negative I, 1. So I cubed is negative I. So 1 times negative I is negative I. So I cubed, I to the 23rd is the same thing as negative I. So let's go ahead and plug that in right here. This is now going to be 3 times negative I. So that's negative 3i times 2 minus 7i. At this point, it turns into exactly what we were doing with this first example right here, where we had a number on the outside of parentheses and we want to distribute that number. So let's try it here. We've got, when we distribute, this will become negative 6i. Okay, and then 2 negatives make a positive. 3 times 7 is 21 times I squared. And again, we don't want to leave an I squared. I squared is the same thing as negative 1. So 21 times negative 1 is negative 21. And then we always want to put the imaginary component last. So this is going to be a minus 6i when I'm finished right here. Okay. All right, one more. And let's see what we can do with this. So let's say that we have 3 plus 5i times 2 minus 7i. Okay. Now notice the difference on this one compared to this one right here. On this one, we were separated with a negative sign, and on this one, we are not. So what have we learned all the way back in Algebra 1 when you have two sets of parentheses and you have to multiply them together? We should FOIL. Okay, so let's try foiling here and let's see what we get. So foiling is, first, 3 times 2 is 6. Times the outside, so 3 times negative 7i is minus 21i. Inside, 5i times 2, that's a plus 10i. And then last, 5i times negative 7i is a minus 35. And I times I is I squared. Okay. All right. Let's clean this up a little bit. Remember, I squared is negative 1. So 35 times negative 1 is a plus 35. There's a 6 at the front. And check out these two terms in the middle. Negative 21i plus 10i. Those are like terms. They both have an I. Negative 21 plus 10 is minus 11i. And last but not least, we can combine these like terms here. 6 plus 35 is 41 minus 11i. So when we FOIL these out, simplify the I terms that don't have a power of 1 and combine like terms, we get to 41 minus 11i. All right, hopefully this made sense for our first video. Like I said, I'm going to include a little bit of practice in the OneNote here. So check that out, try those, and then that'll be all that we have for today. Have a great day, y'all. Talk to you later. Bye.